So in the previous lecture, we have seen the importance of the feedback mechanism. Now we will see the detailed treatment of the designing a state feedback controller. So one important point to note here that whatever the controller design techniques we would see, we will design only for the linear time invariant systems. So we won't be discussing the controller design for the linear time varying systems because it would require more theoretical tools from the non-linear systems for designing the controller for LTV systems. So consider the n-dimensional single variable state equation. By single variable, we actually mean by the input u, where we assume d is equal to 0 to simplify the discussion. So by d, it is not so it should not be confused with the disturbance variable, but this d is basically the distribution matrix of the u. It is this one, du, and this d we have taken 0. So it has nothing to do with the disturbance variable what we have specified in the previous lecture. So in state feedback, the input u is given by u is equal to r minus k times x, where r is the reference signal, and k, since x is a n-dimensional system, so it would be of 1 cross n. Why? Because u is a scalar variable. This whole part can also be represented by this summation I is equal to 1 to n of ki xi. Okay, so each feedback gain ki is a real constant, and this is called the constant gain negative state feedback, or simply the state feedback. Now if we connect this control signal, or if we substitute this u into the model of the plant, we would get x dot is equal to a minus bk in times x plus pr, and y is equal to cx. So we have specified this as closed loop LTI system, and this one is only LTI, which denotes the plant. Okay, so there are many important things which needs to pay attention here, that for this plant the input is u and the outputs are x and y. Okay, if we have the access to the state variable as well. Now when we substitute this u into this equation, we obtain another state space equation where the A matrix becomes A minus bk, and the input to this plant becomes the reference trajectory r. Okay, so what we want to implement, let's say if we see the state space description, that we have the integrator 1 by s, this x dot, and x dot is basically the summation of, we are having A and the gain matrix B, or the gain vector B from here u. Okay, and if I put again C, we would obtain y. Okay, so this you should read as a small c, because it is a single input single output system. So this is the LTI system we have. Now when we implement this u, we have this gain k from x, some very reference trajectory r, which yields a signal u. Okay, so if you say u becomes r minus k times x, and this is the LTI system we have, and this part is basically our controller. Okay, now if I see the overall closed loop system, for the overall closed loop system, the input becomes this reference trajectory r, and the A matrix is changed to A minus BK because of the inclusion of this state feedback. So in the last week we have discussed many tools or many uh, implications of the controllability of the system. So we have one important result here, that this pair A minus Bk comma B for any 1 cross n real constant vector k is controllable if and only if the pair AB is controllable. If meaning to say, if this pair A comma B is controllable, then this new pair where the A matrix has been changed would definitely be controllable, and vice versa, because this is a necessary and sufficient condition. So if we do not draw the controller in the picture, what we have in a, let's say this is the plant with U, and let's say we are having X, so we are assuming for the moment that we have access to X, and by having the access to X we can compute Y always. Okay, now there is some control signal R, sorry, the reference trajectory R. This is the plant, the overall plant description, where the LTI or the model has access to U and X but has no connection with the R. Now if you recall this previous architectural description of the connection between the plant and the controller, we have substitute only this part. So here we have one controller, okay, which is taking some feedback from the states. Now we can show the proof of this important result only by through this structural description of the block diagram. Say for example, see that if how we have computed the signal U. The U is being computed by this formula R minus Kx. Okay, so if U cannot steer the trajectory of X from, let's say, X of T1 to X of T1, then R can never be. Okay, so this is one of, in this way we can see the significance of this theorem, but we can see the formal proof of this statement. So we'll show this theorem by considering a 4-dimensional system where n is equal to 4. So we define the controllability matrix B A B A square B A cube B. So since it's a single input single output system, we know at the outset that the controllability matrix would definitely be invertible. Okay, and the controllability matrix of the feedback system, which we have denoted by this subscript F, it's B A minus with the new state matrix A minus BK in a similar way. Okay, so it is straightforward to verify that the controllability matrix of the feedback system can be expressed as the multiplication of the controllability matrix of the plant into an upper triangular matrix. Okay, you can see some similarity between this matrix and some of the matrices which we have discussed in the tutorial problems part 1 and part 2 of the controllability week. So one important result we have discussed there, that this matrix CF would have the full rank if and only if this C matrix has full rank or it is non-singular. Why? Because this is an upper triangular matrix, and for all case it would definitely be a non-singular matrix. Okay, so note that K is 1 cross n, B is n cross 1, thus KB is a scalar definitely, so is every entry in the rightmost matrix. Now because the rightmost matrix is non-singular for any K, because being the upper triangular, the rank of CA always equals the rank of the controllability matrix. Thus the closed loop LTI is controllable if and only if the plant itself is controllable. Okay, So this recalls the same thing what we have discussed previously, that the input R does not control the state X directly. Okay, but it generates U to control X. Therefore, if U cannot control X, neither can R. Right? So this is another way of seeing the of visualizing that important result. This is another results which we have discussed during one of the tutorial problems of the controllability week, that consider the LTI system with n is equal to 4, that is a 4-dimensional system, and the characteristics polynomial of that LTI system is defined by this, by some coefficients alpha 1, it should be alpha 2, alpha 3 and alpha 4. If the system is controllable, then it can be transformed by the transformation x bar is equal to px when the matrix Q is computed by this. So if you recall, in one of the tutorial problem, we have defined a matrix T, which happens to be a transformation matrix equal to the controllability matrix times another matrix, which is nothing but this one, which is an upper triangular matrix containing some coefficients of this characteristic polynomial. And then we have showed that T is in fact transformation matrix, which not only transform the system from having a state x bar to x bar, but also it gives us the controllable canonical form or the CCF form. So this specific matrix Q or T, what we had seen in the tutorial of part 1 and part 2, into the controllable canonical form, into this form where all the coefficients of the characteristic polynomial will constitute the first row with the negative sign, and the B matrix would transform into B. So suppose if the C bar matrix is given by B1 beta 1 to beta 4, then the transfer function can be expressed as this one. Okay, so we won't see the proof of this theorem, because this is we have already discussed it during the tutorial. Because first of all, we need to show that this Q or P matrix is a non-singular matrix, and it would definitely transform into this controllable canonical form, which we had seen many times earlier. But based on that, this is the most important result where we are actually designing a controller. So it says that if the n-dimensional LTI system is controllable, then by using this state feedback U is equal to R minus Kx, where K is a 1 cross n real constant vector, the eigenvalues of A minus Bk can arbitrarily be assigned provided that complex conjugate eigenvalues are assigned in pairs. So there are many important things associated with this statement, that from the earlier definitions of controllability, we know that if the system is controllable, then there exists a control law. Okay, now if we want to assign some eigenvalues of the closed loop, and we know at the same time that the eigenvalues defines the transients in the steady state properties or the characteristics of the system. So if we have those specifications and we have extracted that at what eigenvalues we want to place the eigenvalues of the closed loop system, then we can take the plant to any eigenvalues by applying this state feedback, or by using this state vector k, feedback vectors k. Okay, and at the same time we need to show that if we are assigning any eigenvalues which is complex eigenvalue, then those complex eigenvalues should occur in as a pair of conjugate pair. Okay, so while seeing the proof of this eigenvalue assignment, first of all there are two things we will demonstrate here, that if the pair AB is controllable, Then we can assign the eigenvalues of the closed loop to anywhere in the left hand side or the right hand side, it does not matter, with using the feedback in k. Now the second part is we will design that k also, that for what the how the k can be designed. Okay, so once again consider, let n is equal to 4. If the plant is controllable, then it can be transformed into the controllable canonical form by using the previous results into having the state with x bar, and so this u bar won't be there because the input would remain the same. Okay, and a bar we have seen many times that a bar can be computed by PAP inverse, where P is the transformation matrix and B bar can be computed as PB. And there is also a relationship between the controllability matrices. So this with a bar sign represents the controllability matrix of this transform pair, and this uh, matrix is of the original LT AB pair, and they are related by this P matrix as well. Okay. So first of all, we substitute x bar is equal to px in u. So this was the original control law, u is equal to r minus kx, and from here we could write x as p inverse of x bar. So we substitute here as p inverse x bar, and we assign kp inverse as k bar. So the control signal becomes u is equal to r minus k bar x bar, where x bar is the state of the transform system, and we have defined k bar as kp inverse, where p is also known to us. Now note that if we see this closed loop system with this control signal, so if I apply this u to this transform signal, we would have the state matrix as a bar minus b bar k bar. Now a bar is nothing but PAP inverse, b bar is PB, and k bar is KP inverse. So if I substitute all these, this a bar, b bar and k bar into this, we would obtain p times p into a minus bk into p inverse, which is nothing but is equivalent to this one, which implies that the eigenvalues of this matrix would definitely be equal to the eigenvalues of this one, because p is nothing but a transformation matrix and both the matrices are related by this transformation under p. It implies, so lambda denotes the eigenvalues, so the eigenvalues of this matrix would definitely be equal to the eigenvalues of this matrix. Now say suppose we are given a set of desired eigenvalues, and using those eigenvalues we can determine the characteristic polynomial of the feedback system. So we need to fix some eigenvalues of the closed loop feedback system. That's why we have used in subscript f, right? So using those eigenvalues we can compute this characteristic polynomial, which is nothing but the determinant of Si minus A of that matrix. And since A is a 4-dimensional, we would have the order of this polynomial, or the degree of this polynomial is 4, with some coefficients alpha 1 bar to alpha 4 bar, right? So we also have this information of this all these coefficients from the given set of desired eigenvalues. Now if k bar is chosen as k bar is equal to alpha 1 bar minus alpha 1, alpha 2 bar minus alpha 2, and so on. So note that here that alpha 1 bar is known to us from the set of given desired eigenvalues. These alpha i's are also given to us, which are the coefficient of the characteristic polynomial of the plant itself. So from there we can compute one vector and we assign that vector to k bar. Okay. Now if we substitute this k bar here, our state feedback equation will become this one. We have a bar already in the transformed way in the controllable canonical form. B bar we would have PB, and k bar we are using this one. So if I substitute all these vectors and matrices into this equation, we would have this A matrix and this B matrix. The C matrix would remain as it is because beta 1 to beta 4 are already of the transform system. Okay. So because of the companion form, the characteristic polynomial of this A bar minus B bar K bar and of A minus BK equals this one. Under any transformation, the eigenvalues does not change. If the eigenvalues do not change, then the characteristic polynomial would also not change. Okay. So thus the state feedback equation would definitely has the set of desired eigenvalues. Now the feedback gain can be computed from this equation where we have substituted Kp inverse as K bar. P is known to us because it is a transformation matrix. K bar we have defined it by using the information of the coefficients of the plant and of the desired feedback loop. So from there we have directly computed K is equal to K bar into P, and P is nothing, you can compute P from here, which is nothing but C inverse into C bar into C inverse. Okay, now we can take the C inverse here because we know we are dealing with a single input single output system. So this controllability matrix would definitely be a square matrix, so we can take the inverse. And now since it involves the inverse of the controllability matrix for the computation of K, this controllability matrix would definitely be a non-singular. So if the system is not controllable, then you cannot compute the K. Okay, because this inverse is already included in the definition of the or in the computation of the feedback K. Okay? So this is one of the very important results. So since we are stressing on this fact that the controllability matrix is a square matrix and the inverse is possible, but if it is a multivariable system, the controllability matrix would no longer be a square matrix. But still it would involve in some way the involvement of the full rank of the controllability matrix. Okay. If we pay attention to the feedback transfer function, that what happens, so once we apply state feedback in the state space analysis, then what would happen to the transfer functions? Given this this ABC pair, we can compute the transfer function G hat as Si minus A inverse times B, and this would be this one. So this transfer function is already specified in one of the earlier results, where alpha i's are the coefficients of the characteristic polynomial of this plant. Now after the state feedback, this pair would change into another A matrix, but the BC would remain as it is. So this is the transfer function of the closed loop system, which we can compute by this one. And finally we would have this transfer function where beta i's would remain as it is, and the numerator polynomial is replaced by another polynomial represented in terms of alpha bar i's. Okay. So there are many important things to note here. So first that in both the transfer functions of the plant and of the state feedback of the closed loop system, the numerators remains the same. If you compute the root of this numerator and of this numerator, the roots would remain the same, which are basically the zeros of the system. So the state feedback can shift the poles of a plant but has no effect on the zeros. So we cannot shift the zeros of the plant, but we have full control over shifting the eigenvalues of the poles of the plant, given that the system is controllable. Right? Now second, the state feedback may alter the observability property. This is the most important part, which you should note at this time. And once we come on to the week where we would discuss the physical significance of the observability, we will explicitly show that how the state feedback can alter the observability property. So now at the moment you can visualize this thing in the sense, say suppose there are some zeros of the closed loop system or of the plant, and in the plant there is no overlapping of the zeros and the poles. Hmm? Now since we can shift the poles to anywhere with the inclusion of the state feedback, it may happen that some of the eigenvalues or some of the poles of the feedback system may overlap with the zeros of the closed loop system. So in that case, those polynomials would cancel out, and whenever that cancellation happen, it means that the system has lost its observability. Okay, but we will see this in the more detail. But at this time, you can see that because one or more poles are shifted to coincide with the zeros of the G hat S. Okay. Now, if you want to compute the gain K in MATLAB, you can use this command K equal place, where A is the A matrix, B is the B matrix, and V is the vector containing the eigenvalues. Okay, so if the pair should be controllable while using this command place, the AB pair should be controllable, and the vector V should have no repeated eigenvalues. Okay, now this command should be used with great caution, and generally avoid this command because it is numerically badly conditioned. Okay.